We've already done motion in a vertical circle. In a motion in a vertical circle, you're talking about the conservation of momentum and the centripetal acceleration. This question is about motion in a horizontal circle, so we just have to find out some key information about this, okay? Vertical rod, BA. B going to A is 4L in length. Fixed to a horizontal surface, and the other end A is vertically above B. So this blue line here is just a rod, okay? Now that we've established that, and we have like a weight that's attached to the rod at two different points and spinning around it, okay? Now, the ends of the light inextensible string, when we're talking about the light inextensible string, we're talking about this red part here. It's one string, not two strings, okay? And its length 4L itself are fixed to A and to a point C, a distance 2L below A on the rod. So this means the following. And it also says the string is of 4L. Okay, that's perfect. And does it say anything about midpoint? To a point C, fixed on A, below C. Okay. So happens here, guys, is this. This distance from here to here is 2L. Would everybody agree with that? Because it says it's 2L below A. So it's very obvious that it is 2L. Now, the other thing is, this triangle here, it's the same length. So where does it say that? It rotates with both parts of string taut, uniform angular mass, so midpoint. Keyword, midpoint. So that means your 4L, which would represent this part and this part, is now cut in half into 2L and 2L. Okay? So 2L and 2L. Now that makes my life a wee bit easy, doesn't it? What type of triangle are we dealing with? We're dealing with a equilateral triangle. 60, 60, 60. Because all three sides are the same length. So 60, 60, 60. Now, if I was to grab this here, yeah. So, I'm just going to work a bit on this graph here now, okay? So, I have my angle alpha. If that's 60, and that's 60, it means my angle alpha here will also be 60 by alternate angles, 60. Okay, so alpha equals 60 degrees. Now, all I have to do is have a choice of two different equations. The first one is the centripetal acceleration. Centripetal force, if you will. I'm going to use F equals m or omega squared because it mentions angular velocity in the question. So that's my choice. I'm also going to use what goes up equals what goes down. So there's two equations coming from that. So that's A and that's B. Now, choose either one to start off with. Might just start off with now just one question. They're going for two different tensions, aren't they? So it means not one string, two strings. So I need to find the part of the language that tells me that. A small mass of mkg is tied to the midpoint of the string. It rotates with both parts of the string taut. Both parts of the string taut in a uniform horizontal circle. Find the tension in each part of the string. It's treating as two pieces of string. The language is in the question, so I would have treated that initially as one piece of string that was threaded through. We've done that type of question before, but here's what stopped me from doing that. That piece of language there, each part of the string means two different tensions, and then he mentions both parts of the string taut. So that language is suggesting two tensions, not one. Okay? So what we're going to do is this. What goes up equals what goes down. So looking at T1 here. Oh, where are you? So T1 goes in this direction here, and that's 60 degrees, T1. So that makes that T1 cos 60 and T1 sine 60 going up and to the left. Then we have T2, which is going down this direction here. And once again, T2 will also be held at 60 degrees. So that'll make that T2 sine 60 and T2 cos 60 going downwards. Okay? Now that we have that, what goes up equals what goes down. So, forces up equals forces down. So what's going up, guys? And we also got to remember our what's it, mg going downwards, isn't it? So mg is going down. What else is going down? Sorry? T2 cos 60? T2 cos 60 going down. And what goes up? It's T1 sine 60. Now, let's sine 60 is root 3 over 2. T1 equals mg plus a half T2. Yeah. They should be the other way around. You're right. Sorry, T1, what's that? T1 sine 60 and T1 cos 60. So that should be a T1 cos 60, shouldn't it? Which is a half T1. Sorry, excuse me about that. Okay, cool. So that's one equation. What's my second equation we were talking about earlier? That's forces up equals forces down. What's the other one? F equals m or omega squared. Now, what forces go towards the center of the circle? The T1 sine 60 does. And what else goes towards the center of the circle? T2 sine 60. They're both tensions. Both tensions have a component acting towards the center of the circle. So what we're going to get is T1 sine 60 plus T2 sine 60 equals m. Do we know the radius? Do we know the radius, yeah? We don't know the radius. So m. Huh? Well, we can. So yeah, we can do it up here. Just give me a second. That there, yeah. So you're right. 2L sine 60. What is 2L sine 60? I think it's just root 3L. It's going to be 2L times root 3 over 2, which is going to be root 3L. So the radius is root 3L. So mr is going to be root 3L times omega squared. Does it give us omega? No. Omega squared. Okay. What's T1 sine 60? Root 3 over 2 T1 plus root 3 over 2 T2 equals root 3 ml omega squared. I have a simultaneous equation of sort, don't I? It's a bit like a simultaneous equation, but I'd like to tidy it up a bit more. I'm going to get rid of all the root 3's. Everybody alright with that? Going to multiply both sides by 2. That's one simultaneous equation. That's the simultaneous equation for centripetal force. I'm then going to work on the other simultaneous equation by multiplying both sides by 2. And what I'm going to get here is T1 equals 2 mg plus T2. T1 minus T2 equals 2 mg. Then I'm going to have both of them lined up nicely now. So I'm going to get 2T1 equals 2 ml omega squared plus 2 mg. Divide everything by 2. T1 equals L m omega squared plus mg. Might factorise out the m just to make it look nicer. Okay, that's T1. To get T2, I'd sooner just redo the full equation. So I'm going to multiply the bottom one by minus 1. So I'm still going to have T1 plus T2 equals 2m L omega squared, but the bottom one's now going to become minus T1 plus T2 equals minus 2 mg. I'm going to get 2T2 ends up to be 2 ml omega squared minus 2 mg divided by 2. T2 ends up to be ml omega squared minus mg. Factorize out the m. L omega squared minus g. Okay. So guys, the two tensions in question are T2 and T1 here. You can see m equals L omega squared plus g, and T2 is m bracket L omega squared minus g. So according to the language there, that's exactly what we're looking for. So that's gone now. At a given instant, both parts of the string are cut. Find the time in terms of L which elapses before the mass strikes the horizontal surface. So what happens when both strings are cut at the same time? Can anybody tell me? It gets fired across, doesn't it? But it's going to sink downwards. Out of interest, doesn't matter how fast it's going directly to the right. That doesn't matter at all, does it? So, if that's the case, then it's a very simple UVAS question. How high are we off the ground? Sorry? We're 3L off the ground, aren't we? Because we agreed earlier that that's a equilateral triangle. We divided it into half. So it's your 2L plus your other L, so it gives us, we're 3L off the ground. So if we use UVAST, we're going to get UVAST. Our initial velocity going downwards is 0. Our final velocity is we don't know what. What's our acceleration? G. Our S value? 3L. And our T value? Our T value is what we're looking for, isn't it? The time. So, what's our option? What formula should we use? Phi equals U plus AT, or phi squared equals U squared plus 2AS? Or what's the other alternative? S equals UT plus a half AT squared. I think that one's going to do it for us. 3L equals a half. Oh no, you didn't. So, shh, keep quiet. So therefore, 3L equals a half GT squared. 6L equals GT squared. T squared equals 6L over G. T equals the square root of 6L all over G. So that's 2013 6b.